At a computer conference in San Francisco in 1975, MOS Technology placed a number on its new microprocessor that seemed almost impossible to take seriously: $25. Intel's 8080 and Motorola's 6800 were selling for prices approaching $200, so the difference was large enough to make some engineers suspicious. Chuck Peddle and a small group of former Motorola engineers were not introducing a toy processor or an educational curiosity. They were offering the MOS 6502 as a usable general-purpose microprocessor at a fraction of what established competitors were charging. Peddle later remembered the introduction with the kind of detail that captured the atmosphere around the launch: chips displayed in glass jars, customers arriving to buy them, and enough disbelief surrounding the price that the demonstration itself became part of the story. The skepticism made sense. In the young microprocessor industry, price carried assumptions about capability. Semiconductor companies were spending heavily to develop increasingly sophisticated chips, and processors were still expensive enough that choosing one could shape the economics of an entire product. A drastic reduction in CPU cost therefore raised a question larger than whether MOS could take sales from Motorola or Intel. It changed what kinds of products designers might attempt to build in the first place. A company that previously could not justify an expensive processor might suddenly reconsider. A hobbyist experimenting with digital electronics faced a different threshold. A small manufacturer designing a terminal, controller, game, or computer no longer had to devote the same portion of its budget to the CPU. None of this guaranteed that the 6502 would create a mass market. A processor alone was not a computer. It still needed memory, support circuitry, storage, software, input devices, a display or terminal, and someone willing to turn all of those pieces into a usable system. Yet removing tens or even hundreds of dollars from one of the machine's central components opened design possibilities that had previously been harder to justify. The price was especially provocative because MOS Technology was not one of the semiconductor giants expected to dictate the direction of the industry. Peddle's group had arrived from Motorola, where members of the team had worked around the 6800 generation, and now they were confronting that world with a processor whose economics seemed almost deliberately disruptive. The immediate effect was pressure. If MOS could really manufacture and sell a capable microprocessor for $25, established prices suddenly became harder to defend, and customers gained leverage they had not possessed before. The deeper consequence was still invisible. There was no Apple II, Commodore PET, or TRS-80 on store shelves yet, and the idea of millions of ordinary people owning computers remained far from certain. In 1975, the 6502 was still just a small piece of silicon entering a market dominated by much larger companies. The important question was how Peddle's team had reached a price that looked unreasonable to its competitors, and why they believed the microprocessor business was serving only the customers wealthy enough to accept the old prices. The answer began at Motorola, where Chuck Peddle had worked closely with the 6800 program and spent enough time with potential customers to see a problem that engineering specifications alone did not solve. The 6800 architecture had already been taking shape before Peddle became involved, and his role centered heavily on understanding how customers might actually use the processor and what prevented broader adoption. Again and again, price emerged as a practical barrier. For many designers, the processor represented too much of the total cost of the product they were trying to build. Peddle became convinced that a much larger market existed below the price level being served by the established semiconductor companies. The opportunity was not necessarily to create the most advanced processor available. It was to create one that could deliver enough capability at a price low enough to change what customers were willing to attempt. That idea increasingly diverged from the economics surrounding Motorola's existing microprocessor strategy. And in 1974, Peddle left the company with several colleagues and joined MOS Technology in Pennsylvania. MOS was far smaller, but it offered something the group needed: the freedom to pursue a processor designed around aggressive cost reduction. The engineers did not simply take the 6800 and strip away random features. They reconsidered what circuitry was truly necessary, how the chip could be made compact enough to manufacture economically, and how its instruction set could remain practical for real systems without carrying the cost structure of its larger rivals. The first result was the 6501, designed to be electrically compatible with systems using Motorola's 6800 bus arrangement, followed by the closely related 6502 with a different pin configuration. That resemblance immediately created legal pressure. Motorola sued MOS Technology in 1975, accusing the company of misappropriating technology and challenging the activities of former Motorola employees who had joined the smaller firm. For MOS, the dispute was dangerous because the company was trying to establish a new processor family while facing a corporation with far greater financial resources. The eventual settlement removed the 6501 from the market and imposed financial costs. But the 6502 survived. That survival mattered because MOS had already demonstrated that the chip's low price could attract attention far beyond conventional industrial customers. To make the processor easier to evaluate and program, the company developed the KM1, a compact single-board computer built around the 6502. It was intended as a development system, complete with a small keypad, hexadecimal display, memory, and interfaces that allowed engineers to experiment with the processor without designing an entire machine first. Hobbyists quickly saw something else. Here was a functioning computer platform that could be purchased, programmed, modified, and understood at a price far below the large systems that had defined computing only a few years earlier. The KIM-1 did not resemble the polished home computers that would soon follow. It lacked the integrated keyboard, video display, storage, and consumer packaging that would make later machines approachable to ordinary buyers. Its importance came from the change in audience. A development board intended to support a low-cost processor was being treated as a computer by people who wanted to explore computing for themselves. Peddle's argument about price was beginning to produce evidence in the real world. Lowering the cost of the CPU had not merely made one component cheaper, it had lowered the threshold for participation. Yet MOS still faced a weakness that price alone could not solve. A new architecture also meant new software, new programming habits, and a new ecosystem that had to be built around it. In California, another group of former semiconductor engineers was preparing a processor that attacked exactly that problem from the opposite direction. The company taking aim at that weakness was Zilog, founded in 1974 by Federico Faggin and Ralph Ungermann after Faggin left Intel. Faggin had played a central role in Intel's early microprocessor development, including the 8080, and Zilog's first major processor was conceived as a way to advance that architecture without forcing existing users to abandon what they already knew. Masatoshi Shima, another former Intel engineer who joined Zilog, became one of the key designers responsible for turning that concept into the Z80. When the processor appeared in 1976, it could execute programs written for the Intel 8080 while adding a substantially expanded instruction set, additional registers, and features intended to make system design and programming more capable. That compatibility immediately gave Zilog an advantage MOS technology could not create through low processor pricing alone: continuity. A designer already familiar with the 8080 did not have to approach the Z80 as an entirely foreign machine, and software, written for the older processor, had a practical path forward instead of becoming useless when a new CPU was chosen. Faggin later described this compatibility as a deliberate way to protect customers' software investment, and the decision gave the Z80 a strategic strength that was easy to overlook when processors were compared only by purchase price. Software had already become part of the economics of computing. Programs had to be written, tested, maintained, documented, and supported. Engineers had to understand the architecture, and development tools had to exist before a new system could become productive. Zilog was therefore competing on more than silicon cost. The Z80 gave customers a way to move ahead without discarding as much of the software, experience, and tooling they had accumulated around the 8080. That made the processor especially attractive to manufacturers and developers who were already invested in that environment. The 6502s approached the market from a different position. Its aggressive price gave designers room to reconsider the hardware budget of an entire machine, but choosing it also meant committing to a new programming architecture and building software around that decision. The Z80 reduced a different kind of friction. Its richer programming resources and compatibility could shorten the distance between an existing 8080 system and a more capable successor. Neither strategy guaranteed commercial success. A processor still needed manufacturers willing to build useful computers around it, software developers willing to support those machines, and customers willing to buy the finished systems. Yet the rivalry had now acquired a second dimension. MOS had shown how far the price of the processor itself could be pushed downward. Zilog was showing how valuable continuity could become when software and engineering knowledge already represented significant investment. By the time the Z80 began reaching system designers, the contest was no longer about which chip looked cheaper on a price list. It was about which architecture allowed a manufacturer to build the more economical, complete system once hardware, software, and development effort were all taken into account. To see why both approaches would soon succeed, the comparison had to move inside the processors themselves. Looking inside the two processors made their different strategies easier to understand. The 6502 was built around a comparatively lean internal design, with a small set of programmer-visible registers and an instruction system that relied heavily on efficient access to memory. Its accumulator and two index registers gave programmers fewer places to keep temporary values than they would find on the Z80. But the architecture compensated through addressing modes that allowed useful work to be done with compact instruction sequences. Zero page, the first 256 bytes of memory, could be accessed with especially short instructions, and often served as a fast working area for frequently used values. These choices also supported an important manufacturing advantage. MOS Technology designed the 6D502 to occupy relatively little silicon area, and the company's fabrication process achieved unusually high yields. More usable dies could be obtained from each wafer, while fewer defective chips had to be discarded. That combination of compact design and strong manufacturing yield was a major reason MOS could price the processor so aggressively without reducing it to an underpowered curiosity. The Z80 used its transistor budget differently. It offered a much larger collection of registers, additional instruction forms, and capabilities extending what 8080 programmers already understood. Register pairs could hold 16-bit values. Alternate register sets provided additional working storage, and index registers supported operations that had no direct equivalent in the original 8080. Zilog also incorporated dynamic memory refresh support into the processor, reducing some of the external circuitry required in systems using DRAM. That greater internal complexity could be worthwhile when the complete machine benefited from simpler, surrounding hardware, or when programmers could keep more intermediate data inside the CPU rather than repeatedly moving it to memory. Even clock frequency resisted direct comparison. A Z80 running at a higher nominal frequency was not automatically faster than a lower clocked 6502 because the two designs organized instruction execution differently and often required different numbers of cycles to complete equivalent work. Performance depended on the software, memory system, chosen instructions, and the way each machine was designed around its processor. The practical consequence was that neither architecture could be judged by a single specification. The 6502 gave manufacturers an unusually economical processor around which to build tightly cost-controlled systems. The Z80 offered greater internal programming resources and a path that preserved much of the 8080 software world. By 1977, those differences were about to stop being engineering arguments. Apple, Commodore, and Radio Shack were preparing complete computers that would put both approaches in front of ordinary buyers. In 1977, those engineering choices finally escaped the laboratory and entered the consumer market. 3 machines arrived that year with very different personalities, but together, they made one fact impossible to ignore. The microprocessor was no longer waiting for a future market. It was beginning to create one. The Apple II used the 6502 inside a machine that Steve Wozniak had designed with color graphics, expansion slots, and a level of flexibility that encouraged owners to keep adding to it. Commodore's PET also used the 6502, but presented a different idea of personal computing. An integrated system with keyboard, display, cassette storage, and processor in one enclosure, built for people who wanted something closer to a complete appliance than an electronics project. Radio Shack's TRS-80 chose the Z80 and gained an advantage neither Apple nor Commodore could easily reproduce. Thousands of retail stores already spread across the United States. That distribution network mattered as much as any register or addressing mode. A customer who had never attended a computer club or ordered a kit through the mail could walk into a familiar electronics store, see a working machine, and buy one. Tandy initially expected modest demand, but the response quickly exceeded those expectations. The TRS-80 reportedly sold around 10,000 units in its first month, far beyond the company's original projection for the first year. The significance was not that the Z80 had suddenly beaten the 6502, or that the 6502 had proved cheaper. Silicon automatically produced the better computer. The processors were now embedded inside complete products whose success depended on far more than the CPU. Apple benefited from Wozniak's system design and the machine's expandability. Commodore benefited from its growing control over both semiconductor and computer manufacturing. Radio Shack benefited from retail reach, recognizable storefronts, and an ability to place the TRS-80 in front of customers who might never have encountered a hobbyist machine. Price still mattered, but it had become one part of a larger equation that included memory, storage, software, displays, documentation, peripherals, and ease of purchase. The 6502's low cost gave designers room to spend money elsewhere or push the final machine toward a lower price. The Z80's compatibility and programming environment gave manufacturers another kind of leverage, particularly when they wanted access to knowledge and software already developing around the 8080 family. What changed in 1977 was the scale of the test. Before then, engineers could argue about instruction sets, chip costs, and development effort in abstract terms. Now thousands of buyers were choosing actual computers, built around those decisions. Each successful system encouraged more programmers to write software. Each new program made the hardware more useful. Each new user increased the incentive for peripheral manufacturers, retailers, publishers, and software companies to support the platform. The processor rivalry was beginning to generate consequences beyond semiconductor sales. A cheap chip could help a manufacturer build a computer. A successful computer could create an ecosystem. Once that happened, the cost of the CPU was no longer the only thing holding a customer inside the platform. Software was about to become the next source of power, and in that contest, the Z80 entered with an inheritance the 6502 family could not simply duplicate. That inheritance became more valuable as personal computers shifted from machines people admired to machines they expected to use. Hardware could attract a buyer, but software determined what happened after the machine reached a desk. Programs for accounting, word processing, database work, programming, education, and games could transform an inexpensive computer into something worth keeping, and every successful platform created pressure for more of them. Here, the Z80 benefited from its connection to the Intel 8080 world in a way that processor price alone could not reproduce. Software written for the 8080 often had a practical path onto the Z80, and developers already familiar with that programming environment could transfer much of their experience. The effect became especially important around CP/M, the operating system created by Gary Kildall in digital research for 8080 class microcomputers. CP/M did not make every Z80 machine automatically compatible with every other one, and it did not dominate all of home computing. Different computers still used different displays, keyboards, disk systems, memory layouts, and peripheral hardware. Yet CP/M introduced a powerful idea. Software could be separated from some of the details of the underlying machine well enough to move across a broad range of systems with comparatively limited adaptation. Its BIOS layer allowed manufacturers to handle machine-specific hardware, while applications relied on a more consistent operating environment above it. For businesses and software developers, that reduced the risk of writing a program for only one narrowly defined computer. The Z80 fit naturally into this growing ecosystem because it could execute 8080 code while providing additional capabilities of its own. The processor did not create CP/M's success by itself. The operating system, disk drive adoption, software publishers, hardware manufacturers, and the growth of business microcomputing all contributed. The advantage lay in alignment. Z80-based systems could participate in an expanding software world without requiring developers to abandon everything that had already been built around the 8080. The 6502 family developed differently. Apple II, owners could not simply take a CP/M program and run it on the native 6502. Commodore systems faced the same architectural divide. Those platforms had to attract software written specifically for their machines or find other ways to bridge the gap. Apple's rapidly growing installed base helped make that possible. Developers followed users, and users followed useful programs, creating the same reinforcing cycle through a different route. The arrival of VisiCalc on the Apple II in 1979 demonstrated how powerful that cycle could become. A single application could make a particular computer valuable enough that customers bought the hardware because of the software rather than the processor inside it. Apple II users also gained access to the CP/M world through third-party Z80 hardware, most notably Microsoft's Z80 SoftCard, introduced in 1980. By placing a Z80 processor on an expansion card inside the Apple II, Microsoft gave owners a practical way to run CP/M software without replacing the computer they already had. That solution revealed how quickly processor architecture and software ecosystem were becoming separate strategic questions. Compatibility could be extended when enough commercial incentive existed. By the end of the decade, neither low-chip cost nor inherited instruction compatibility could explain success by itself. A processor helped establish the possibilities of a platform, but applications increasingly determined whether those possibilities mattered to users. That shift might have favored the Z80 indefinitely if the contest had remained primarily about software portability. Commodore was preparing to change the economics again by controlling something few computer manufacturers possessed: the company that made the processor itself. Commodore's answer was to attack the cost structure of the entire computer, rather than depend on the processor alone. In 1976, the company acquired MOS Technology, bringing the semiconductor operation that produced the 6502 under the same corporate roof as a manufacturer already looking for a way into the computer business. That ownership gave Commodore an unusual degree of control. Most computer companies had to purchase processors and other chips from outside suppliers, negotiate component prices, and absorb another company's margin before they could begin calculating the retail price of a finished machine. Commodore could approach the problem from much closer to the silicon. The PT demonstrated the first important result of that arrangement, combining a 6502-based system with display, keyboard, cassette storage, and memory in a single enclosure. Yet the larger opportunity appeared when Commodore pushed beyond the relatively expensive early personal computer market toward households that had never considered buying a programmable machine. The VIC-20, introduced internationally around the beginning of the 1980s, reflected that shift. It was not simply a cheaper PET. Commodore designed and marketed it as a consumer product that could move through ordinary retail channels. lowering the financial and psychological barrier between computers and people who did not identify themselves as computer hobbyists. Control over MOS-derived semiconductor technology helped Commodore manage component costs, while its expanding manufacturing scale put additional pressure on the final price. That strategy became even more aggressive with the Commodore 64. Introduced in 1982, it used the 6510, a processor derived from the 6502 with additional input-output capability integrated into the chip. The machine also relied on specialized MOS-designed graphics and sound hardware, allowing Commodore to combine a familiar low-cost processor lineage with capabilities that made the complete system far more attractive for games, education, and home programming. The significance was not that the 6510 somehow defeated the Z80 in raw processor terms. Commodore was increasingly competing on a different level. By controlling important parts of its semiconductor supply, designing much of the hardware internally, producing computers at large scale, and fighting aggressively on retail price, the company could force rivals to compete against the economics of an entire vertically integrated platform. Jack Tramiel's famous emphasis on building computers for the masses, not the classes, captured the direction, but the strategy mattered because Commodore repeatedly translated it into cheaper finished machines rather than leaving it as a slogan. The original logic behind Peddle's low-cost processor had now expanded far beyond the $25 6502. The question was no longer whether a CPU could be made inexpensive enough for new designers to experiment with. It was whether ownership of the technology, manufacturing capacity, and distribution could make a complete computer inexpensive enough for millions of people to bring home. Commodore was proving that this was possible, but its success did not close the market around the 6502 family. The Z80 was spreading through a much less centralized world, carried by manufacturers that did not share Commodore's vertical integration, yet were finding their own ways to drive computer prices downward. In Europe, especially, that decentralized expansion would give the Z80 a reach that no single company could easily control. The Z80's expansion followed a very different pattern from Commodore's tightly controlled 6502-based ecosystem. No single company owned the architecture's destiny in quite the same way. Zilog supplied the processor, but manufacturers across different countries built their own machines around it, often with radically different ideas about what an affordable computer should be. That decentralized spread became especially visible in Britain. In 1980, Sinclair introduced the ZX80, a remarkably inexpensive home computer built around the Z80. It could be purchased as a kit or assembled system, used in ordinary television as a display, and reached a price level that made programmable computing accessible to buyers who would never have considered a more expensive machine. Around 50,000 ZX80s were sold in Britain, enough to prove that low-cost home computing did not require the vertically integrated model Commodore was pursuing. Sinclair followed with the ZX81, and then, in 1982, the ZX Spectrum, another Z80-based machine that became one of the defining European home computers of the decade. The importance of these systems lay less in processor specifications than in how many manufacturers could use the Z80 to pursue their own price points, markets, and product identities. Radio Shack had already done so in the United States with the TRS-80. Sinclair did it through aggressive cost reduction in Britain. Other companies adopted the same processor family for machines aimed at business, education, hobbyists, and games. That breadth gave the Z80 an influence that did not depend on one dominant computer manufacturer. Yet the same spread exposed a limit in the idea of processor compatibility. A common CPU did not create a common computer. Two machines could both contain a Z80 and still be unable to run each other's software because the processor was only one part of the system. Graphics hardware could differ. Memory might be arranged differently. Keyboards, storage interfaces, sound hardware, firmware, operating environments, and display routines could all be machine-specific. The Z80 preserved continuity with the Intel 8080 instruction set, but it did not standardize everything surrounding the processor. The same principle applied to the 6502 family. An Apple II-based Tollwitz Commodore 64 and Atari 8-bit computer could share architectural ancestry while remaining separate software worlds. By the early 1980s, the market had therefore become a patchwork of systems that sometimes shared processors, yet differed enough in the surrounding hardware and software to require their own applications, peripherals, and developer knowledge. That fragmentation complicated life for users and programmers, but it also revealed how rapidly the industry had expanded. Manufacturers no longer needed to wait for a single dominant machine design before entering the market. Cheap microprocessors let them experiment with different keyboards, displays, storage systems, graphics capabilities, sound hardware, and retail prices. Consumers gained choice, but every purchase increasingly tied them to a particular platform rather than merely to a processor family. The 6502 and a Z80 had both succeeded widely enough that the rivalry no longer produced one unified market. It produced many competing markets built on top of inexpensive silicon. By then, asking which processor had won could no longer be answered by counting chips alone. The Z80's expansion followed a very different pattern from Commodore's tightly controlled 6502-based ecosystem. No single company owned the architecture's destiny in quite the same way. Zilog supplied the processor, but manufacturers across different countries built their own machines around it, often with radically different ideas about what an affordable computer should be. That decentralized spread became especially visible in Britain. In 1980, Sinclair introduced the ZX80, a remarkably inexpensive home computer built around the Z80. It could be purchased as a kit or assembled system, used in ordinary television as a display, and reached a price level that made programmable computing accessible to buyers who would never have considered a more expensive machine. Around 50,000 ZX80s were sold in Britain, enough to prove that low-cost home computing did not require the vertically integrated model Commodore was pursuing. Sinclair followed with the ZX81, and then, in 1982, the ZX Spectrum, another Z80-based machine that became one of the defining European home computers of the decade. The importance of these systems lay less in processor specifications than in how many manufacturers could use the Z80 to pursue their own price points, markets, and product identities. Radio Shack had already done so in the United States with the TRS-80. Sinclair did it through aggressive cost reduction in Britain. Other companies adopted the same processor family for machines aimed at business, education, hobbyists, and games. That breadth gave the Z80 an influence that did not depend on one dominant computer manufacturer. Yet the same spread exposed a limit in the idea of processor compatibility. A common CPU did not create a common computer. Two machines could both contain a Z80 and still be unable to run each other's software because the processor was only one part of the system. Graphics hardware could differ, memory might be arranged differently, keyboards, storage interfaces, sound hardware, firmware, operating environments, and display routines could all be machine-specific. The Z80 preserved continuity with the Intel A280 instruction set, but it did not standardize everything surrounding the processor. The same principle applied to the 6502 family. An Apple II, Commodore 64, and Atari 8-bit computer could share architectural ancestry while remaining separate software worlds. By the early 1980s, the market had therefore become a patchwork of systems that sometimes shared processors yet differed enough in the surrounding hardware and software to require their own applications, peripherals, and developer knowledge. That fragmentation complicated life for users and programmers, but it also revealed how rapidly the industry had expanded. Manufacturers no longer needed to wait for a single dominant machine design before entering the market. Cheap microprocessors let them experiment with different keyboards, displays, storage systems, graphics capabilities, sound hardware, and retail prices. Consumers gained choice, but every purchase increasingly tied them to a particular platform rather than merely to a processor family. The 6502 and Z80 had both succeeded widely enough that the rivalry no longer produced one unified market. It produced many competing markets built on top of inexpensive silicon. By then, asking which processor had won could no longer be answered by counting chips alone. Return to San Francisco in 1975, to the table where MOS Technology offered the 6502 for $25. At the time, the price looked almost implausible. The processor industry was still young. Established chips cost far more, and there was no guarantee that inexpensive silicon would create a mass market for personal computers. Yet within only a few years, that assumption had been overturned. Microprocessors from the 6502 and Z80 families were appearing inside machines that could be bought by hobbyists, students, families, programmers, schools, and small businesses. The importance of that transformation was larger than any single benchmark of technical superiority. The 6502 and Z80 reached the market through different strengths, different companies, and different ecosystems, but together they helped lower the barriers that had kept computing concentrated among institutions, specialists, and people willing to spend far more money than the average household could justify. What began as a dispute over processor economics had expanded into something much larger: complete computers competing on price, software, accessibility, and usefulness. By the early 1980s, the most important question was no longer whether an ordinary person could own a programmable computer at all. It was which one they would choose. That change is the real measure of what the 6502 Z80 era accomplished. The $25 chip on that 1975 table did not win the entire processor market, and the Z80 did not need to lose for the revolution to happen. The rivalry helped create enough pressure, enough experimentation, and enough affordable hardware that personal computing crossed a threshold it could not easily reverse. The processor battle mattered because it shifted computing away from being defined only by what engineers and corporations could build and toward what ordinary people could realistically afford to own.